So now that we've seen the fundamental theorem part 1, we can move on to the fundamental theorem part 2, which that name has always freaked me out because fundamental seems like there should only be one, but apparently there are 2 of them. So fundamental theorem, we have talked about area under the curve. We've been talking about it for a week or so now. And we're going to talk about this thing called the area function. So if you take a look at the picture that I've got there, we've got a function, f of t, that's the curve that kind of rolls up and down here, and then a of x is the area function, and that's the accumulated area starting at a set point a and then ending at a variable point x. Okay, so I'm going to write down exactly what that notation means. Okay, so a of x is the area function. It is the area under f of t from a to x. So again, a is something that's set. You know, it might be 0, it might be 3, and then x moves. X is a variable. Okay, so this is given as the integral from a to x of f of t. And then we're going to say dt. So since we use the variable x here, we switch this one to a different variable just to kind of keep everything straight. Okay, so sometimes we can find a formula for the area function. So in this case, for instance, if we want to know, hey, we're looking at the function t cubed, we're starting our lower bound at 2, we want to come up with a formula. So instead of taking a new integral every time, like say we want the area from 2 to 3, and then we want the area from 2 to 7, or 2 to 10, instead of doing an antiderivative, doing the first fundamental theorem over and over and over again, we can come up with a formula just once, and then you can plug in whatever your upper bound is. All right, so that works like this. So remember the way the first fundamental theorem works. We take the antiderivative, which is 1/4 t to the 4th, and then we evaluate it from 2 to x. So we first plug in our upper bound, 1/4 t to the 4th, and then minus, then we plug in our lower bound. So 2 to the 4th is 16, a fourth of 16 is 4. All right, so there's our formula. Okay, so that is the formula that we're interested in. So like I said, whatever, oh, sorry, this should have been an x that I plugged in. Sorry. Okay, so whatever upper bound we use. If we want to use the area from 2 to 4, we would just plug in a 4 for x. If we want to know the area from 2 to 20, we would plug in a 20 for x. The area from 2 to 2 is supposed to be 0, so let's check it out. Say I do plug in a 2 here. 2 to the 4th is 16, a fourth of 16 is 4. 4 minus 4 does in fact give us 0. So you see how it's kind of convenient to have that, because then we can plug in whatever upper bound we want just into this function, and we don't have to do this process all over again. So this is an area function. It represents the area under t cubed, starting at 2 and ending at whatever value of x we want to use. All right, so find a prime of x. If we take this function right here and we take the derivative of 1/4 x to the 4th is x cubed, and then the derivative of 4 just gives me 0, so minus 0, so that of course simplifies to x cubed. Okay, so the connection that we're looking for here is the comparison between t cubed and x cubed. Now notice what we did. We found this area function, and then we took the derivative of it. So basically we took an integral, and then we took its derivative, and we landed right back at the same function. Not the exact same function, but a t cubed for an x cubed, that's pretty much the same. Okay, so that general idea leads us to the second fundamental theorem of calculus. Okay, so start with this. Of course, f of x is continuous on an interval I, and let's talk about some point a in the interval I. Then, here's what's true. If we want to take the derivative of the integral from a to x of some function f of t, what we're going to end up with every single time is f of x, which is the original function, but with an x plugged in instead. And that's exactly what happened here. We took the antiderivative, we plugged everything in, we got our area function, and then when we took the derivative, we landed right back at our original function, but with an x plugged in instead. Okay, so that's our fundamental theorem. We're going to start with what we call an initial condition, and an initial condition is this. The area function, if we plug in a, just gives us 0. And we kind of talked about that right here. If we go from a to a, yeah, we're going to have an area of 0. No area has accumulated at all. All right, so basically what this initial condition says is the area under f of t from A to A is 0, which should make sense. If the interval doesn't have any width, then it couldn't possibly accumulate any area. Okay, so we're going to set up, we see the word proof and we freak out because we think of, two-column proofs from geometry. That's not what we're doing here. I'm just going to kind of lay out in a more formal way why you should believe that this theorem actually works. Okay, so let me show you. So if we start with this, start with the area function. Here's what ends up happening. So we do the first fundamental theorem. We take the antiderivative, which we've been using as capital F, and we evaluate it from a to x. Keep in mind that x is a variable and a is a set constant. So we end up with, we plug in the upper bound, which is our variable x, and then minus, then we plug in our lower bound, which is just going to be a constant. Okay, so here's the important part of the theorem, all right? Something that I want to remind you guys of. This piece right here is going to be a constant. No matter what a is, no matter what the function is, when you take a derivative and plug in a constant, or an antiderivative and plug in a constant, you're going to get a constant. Okay, that's huge when we're working through the proof. Okay, so this is first. This is our area function. It's given by whatever this is, and we're going with very generic terms here. Okay, so now let's say I take the derivative. Taking the derivative of this thing right here, which is the theorem that we're working on, means taking the derivative of this thing right here. Okay, so remember the derivative of capital F is lowercase f of x, and then the derivative of this is 0. So technically we've got this little minus 0, which of course just turns out to be f of x. So hopefully that makes sense to you. Hopefully that makes sense why we have the results that we do in the second fundamental theorem. Okay, so it's kind of a big deal because there are many functions that we can't take the antiderivative of, such as the example that we're looking at right here. Okay, so if I want to know f of 0 means I'm going right into this function, and I'm going to plug in 0 for x. Okay, so the antiderivative from 0 to 0 of the square root of t squared plus t. Now, square root of t squared plus t, not something that we can take an antiderivative of. It might seem like it could be like an undoing the chain rule sort of situation, but remember I would have to have this derivative present, and I don't. So I cannot take the antiderivative of this. But, lucky us, they're asking us to go from 0 to 0. No matter what this function is, if I don't go from a point to a point, my area can't be anything other than 0. Okay? Next, f prime. If I want to know what f prime is, remember, let's write a little side thing here. F prime of x is just f of x, which is this function with an x plugged in. That's exactly what the second fundamental theorem tells me. Because if I take the derivative of an antiderivative, those are opposite operations. They're essentially going to cancel each other out. The only change I see is that the variable gets swapped out, but the function's the same. It's not like it even matters what the variable is when I go to try to plug something in anyway. So I'm going to plug in the 0 to my derivative function, which is right here. So square root of 0 squared plus 0, of course, gives me 0. I can do the same thing with a 3. F prime is the derivative of the integral, which just leaves me with this function. But now I'm going to plug in a 3. Okay, so 3 squared is 9, plus 3 is 12. So I want to simplify this to 2 root 3. Okay, so kind of a simple application of what the second derivative looks like. All right, so we've got a couple of those values there. Next thing I'm going to look at is looking at an area formula. Okay, so those functions that I've got right there in the next section, those are things that you actually can take the antiderivative of. But then, like I mentioned, we're going to talk about functions that you couldn't possibly take the antiderivative even if you wanted to. Okay, so if I wanted to know what the area is under this function from 2 to some random number, that's what I'm going to figure out. I'm going to take the antiderivative of this. Antiderivative of t squared is 1/3 t cubed. Antiderivative of t is 1/2 t squared. Now remember, definite integration does not need a plus c. So I'm going from 2 to x. So first plug in the x. Minus, and then plug in the 2. So 1/3 of 2 cubed, it's 8/3, minus 1/2 of 2 squared, leaves us with 2. Okay, so we can always simplify this up. So we've got 1/3 x cubed minus 1/2 x squared. And then here I end up with 2/3 when I subtract this, because it's 8/3 minus 6/3. So I end up with minus 2/3. So if I wanted to know the area from 2 to 5, for instance, I would just plug the 5 right into this equation. All right, let's do another one. The area under cosine from pi over 4 to some variable value. So antiderivative of cosine is sine. Then I go from pi over 4 to some variable x. So I've got sine of x and then minus the sine of pi over 4. So I want to simplify this down. So sine of x stays the same, and then minus the sine of pi over 4 is root 2 over 2. All right, so remember, if I wanted to know the area from pi over 4 to pi, I could just plug the pi right in here, and it would give me my area instantly, and I wouldn't have to do the fundamental theorem again. Okay, a couple more of these problems, then we've got a cool picture for you to look at. So express this antiderivative f of x of lowercase f of x satisfying the given initial condition. Okay, so I know I want to set it up as an integral, so it's going to be the integral, so capital F of x, remember, is the antiderivative of this. So it's going to be the integral from something to something. And then I always know in here I have t's instead of x's, dt. And what this is telling me is if I plug in 3, I get 0. So I know my upper bound is always going to be an x. If I plug in 3 to this function and I get 0, that means that my lower bound must be a 3. Because if I plug in 3, the integral from 3 to 3 would give me 0. Okay, so this is the antiderivative, meaning if I take the derivative of this, I get this right here. So we're kind of working our way backwards. All right, so it's kind of a weird one, but let me walk you through it one more time. Antiderivative of this. So it's basically the opposite process of what we were doing up above on the top half of the page. So if I take the antiderivative, I get right here. If I were to take the derivative of this, I land back here, according to the fundamental theorem. And the reason I had to include this initial condition is so I know what my lower bound would be. All right? Now these next two examples are very important because people get the idea that they can take the antiderivative and then plug things in. Okay, this one you can't take the antiderivative. You just can't. There's nothing that would let you do that because you've got this nested function of t squared, which would mean you need to have a 2t in the integrand somewhere, and you don't. However, we do have the second fundamental theorem. And the second fundamental theorem tells us if I take the derivative of an antiderivative, all I've got to do is plug the x in. Okay, so all I've got to do is plug the x in. And that's my answer. Okay, so some of them are as simple as that. I want to take a look at this next one, talk about what's different. So this one, the reason that this one is different is because I've got an upper bound of x cubed. All right, so you might think like, oh, well, you know, maybe it works the same way. Maybe I can just plug the x cubed in. However, we don't know because this is kind of new territory, something that we haven't dealt with before. So we're going to walk through this one the long way. And luckily for us, we can take the antiderivative of secant tangent. Okay, so start with the d by dx, and then I'm going to work on getting a formula for the inside here. Okay, so on the inside, the antiderivative of secant tangent, which means what gives us secant tangent as a derivative, and that would be secant. Okay, and I want to run it from 1 up to x cubed. Oops, made my parentheses a little big. That's okay. D by dx of, okay, so I do secant of x cubed, and then minus the secant of 1. That's going to be my area formula, but then as part of this, I need to take the derivative. Okay, so let's take the derivative. Derivative of this is going to require a chain rule because it's the secant of, and then I have this nested function. So derivative of secant is secant tangent. So we have secant x cubed, tangent x cubed, because I always leave my function nested in place there, and then times the derivative of my nested function, which is a 3x squared. Okay, and then secant of 1, first of all, I don't know what secant of 1 is. Second of all, I don't care what secant of 1 is. All I need to know is that it's a constant. And I know that the derivative of any constant is going to give me 0. So this is my derivative. Just going to clean it up a little bit, put the 3x squared first. Okay, so this is the derivative that I asked for here. Now, this one, with my upper bound of x, all I had to do was plug in the x, and that's what I got. This looks very similar. Like if I just plugged in the x cubed, it would give me this much. But what about that part? Well, that part is the derivative of my upper bound. Okay, so again, what I did is I plugged in the x cubed, but then I multiplied by the derivative of x cubed, which is 3x squared. I'm technically doing the same thing here. I plugged in the upper bound, which is x, and then I multiplied by the derivative of x, which of course is 1. All right, so that is the chain rule. The chain rule for the second fundamental theorem is what I just displayed there. So if I take the derivative of the antiderivative from a to g of x, so some fancy function, not just an x, but something like an x cubed, then what I get is similar. I have to do this part still. I plug in my upper bound right into this function, but then I multiply by the derivative of the upper bound. Okay, so that's the chain rule. Let's practice it one more time here with this example. So derivative of the antiderivative, I follow the second fundamental theorem, I take my upper bound and I just plug it right in, but since my upper bound is something other than just an x, I have to multiply by its derivative. All right, so the derivative of 1 over x is negative 1 over x squared. Because this is really x to the negative first, so I move the negative 1 out front, drop the power down to negative 2. All right, I'm going to write that in a better order. Okay, so that is what I get here, the derivative of the antiderivative. It's very similar to the inner function, but because of my 1 over x, I have to multiply by 1 over x's derivative. All right, so this stuff is just kind of some very cool info on what we know about the area function and why on earth we even care about taking the derivative of this function. Because you might be like, okay, cool, so I'm taking the derivative of an antiderivative and it might not mean much to you, but this will hopefully help you to figure out. Okay, so let's talk about this function right here. This is my function f of x. This is kind of like the picture I had on the front. So this is my original. I've got f of x here. F of x is above the x-axis, below the x-axis, above the x-axis. My area function is the accumulating area under the curve. Okay, so now this is the area function. This tells you how your area is changing. All right, so let me walk you through some comparisons, how the graph above compares to the graph below. All right, so I want to write, just so we remember what a of x represents, a of x is the integral from 0 to x. Let's say with this one, since we're looking at this picture, it appears to be starting at 0. So let's make things more specific. Okay, so this curve right here, this is our function f of x. Okay, whenever f of x is above the x-axis, okay, that's this region right here. Whenever f of x is above the x-axis, this is all positive area. So as I move from here to here, I'm just gathering more and more area. Okay, just picking up area as I go. As I move from left to right, I'm accumulating more and more positive area. So whenever f of x is above the x-axis, a of x is increasing. Okay, meaning I'm accumulating area. Okay, now, pieces like this, where f of x is down below the x-axis. When f of x is down below the x-axis, this is negative area. So I end up losing overall area. You can consider it to be losing overall area or accumulating negative area or whatever. Either way, my accumulated area actually ends up decreasing at this point. So I pick up all this positive area and then I start picking up negative area. So my overall area is going to start going down. And then again, when f of x starts increasing, my area starts picking up again. All right, so those are hugely important. So here I'm losing positive area, or again, accumulating negative area, but accumulating negative area is kind of a weird idea. So then we've got these other points here. Let's relate this down to my a of x graph. When f of x is positive, a of x is increasing. When f of x is negative, a of x is decreasing, and then we have one more, f of x is positive, a of x is increasing. Last thing, these maxes right here. A of x has a local max where f of x switches from positive to negative. And then a local min right here where f of x switches from negative to positive. Sorry about that. Okay, so let's compare these pictures that we've got here. All right, so right here I've got positive area. I'm accumulating all this positive area under my positive function, and then right here, this is the most area I'm going to have for a little while, because now I start accumulating negative area. Then this is the least amount of area that I'm going to have for a while, because afterwards I start picking up positive area again, which translates down to the max and min. Let's pretend for a second that this is the velocity function, and we're talking about displacement instead of area. If this is positive velocity, that means I'm moving forward. We consider this a local max because you're kind of the farthest to the right that you're going to be for a while. Then you start moving backward, and you're accumulating all this negative area, and so at this point, this is going to be the farthest to the left that you're going to be in a while. Then we start going forward again, you're picking up positive area, positive displacement, I guess. So if we compare these, the reason that these graphs relate to each other so wonderfully well is because f of x is the derivative of a of x. Okay, f of x is the derivative of a of x. So, picture if you're looking at original function and its derivative, these are all the things you see. When a function is increasing, its derivative is positive. When a function is decreasing, its derivative is negative. When a function has a local max, its derivative is going from positive to negative. When a function has a local min, its derivative is going from negative to positive. So in case you're wondering why on earth we cared about taking the derivative of the area function, this is why. It tells us how the area is changing. Do you have a maximum value? Do you have a minimum value? Is your overall area increasing, decreasing? So this is going to be very, very, very important to the AP problems, which is why we're going to have a whole day on 5.3 and 5.4 AP problems, because this is a huge topic. All right.